Hello, my name is Jeff Christians, and I'm a PhD candidate in the Kamat Laboratory in the Department of Chemical and Biomolecular Engineering at the University of Notre Dame. Today I will be talking to you about some of our recent work looking at the whole transfer process between antimony sulfide and copper thiocyanate. Solid-state quantum dot solar cells are of interest due to their potential for high-efficiency, low-cost photovoltaics. In particular, antimony sulfide provides a broad absorption of visible light due to its 1.7 eV band gap and has shown promising power conversion efficiencies. In our lab, we constructed antimony sulfide solar cells on a mesoporous titanium dioxide substrate using a solid-state copper thiocyanate hole conductor, as shown in the cartoon at the left. These antimony sulfide copper thiocyanate solar cells show peak external quantum efficiencies over 70% and power conversion efficiencies as high as 3.3%. However, there needs to be a fundamental understanding of the limiting factors in these solar cells in order to facilitate the fabrication of higher efficiency devices. Toward this end, we investigated the dynamics of the charge separation mechanism in these antimony sulfide copper thiocyanate solar cells. In these cells, the four basic electron transfer reactions are 1. The excitation of antimony sulfide forming our exciton, and 2. Non-radiative recombination of the exciton. This exciton can also decay through 2 charge transfer reactions. 3. Electron transfer from antimony sulfide to our electron conductor, TiO2, and 4. Hole transfer from antimony sulfide to the hole conductor, copper thiocyanate. In the present study, we used time-resolved transient absorption spectroscopy to probe these reactions. To probe the electron transfer reactions in our antimony sulfide copper thiocyanate system, we employed 4 films: titanium dioxide films coated with antimony sulfide with and without copper thiocyanate, and SiO2 antimony sulfide films with and without copper thiocyanate. Unlike the mesoporous films used for high-efficiency solar cells, in these films, antimony sulfide was deposited on planar TiO2 and SiO2 substrates, as shown, to allow for the precise control of the antimony sulfide layer thickness and minimize absorption and scattering to facilitate spectroscopic measurements. The steady-state absorption spectra of the TiO2 antimony sulfide and SiO2 antimony sulfide films are shown in Figure E and reveal 2 distinct excitonic peaks at 650 and 450 nanometers, indicative of crystalline antimony sulfide. Time-resolved difference absorption spectra were recorded on all 4 films studied over a time window from 0 to 1500 picoseconds following a 387 nanometer laser pulse excitation. As in the spectra of the TiO2 antimony sulfide film shown at the left, all 4 films studied exhibited a broad sulfide radical induced absorption above 500 nanometers, with a peak at 560 nanometers, as well as the photobleaching of the 2 excitonic peaks at 450 and 650 nanometers. Looking more closely at the kinetics of this transient absorption signal, we see a correspondence between the decay of the photobleaching at 460 nanometers, shown here in black, and the growth of the sulfide radical induced absorbance at 560 nanometers, shown here in red. This indicates that both of these signals arise due to a trapping of valence band holes in the antimony sulfide as sulfide radical, as shown in this reaction here. To obtain the kinetics of this hole trapping event, the decay at 460 nanometers was fit using a bi-exponential model, and the rate of hole trapping was calculated as the inverse of the short lifetime of this decay. Using this method, it was found that photogenerated valence band holes in antimony sulfide are trapped as a sulfide radical species with an estimated exponential rate constant of 4.5 times 10 to the 11th per second. To determine the rate of hole transfer from antimony sulfide to copper thiocyanate, TiO2 films with and without copper thiocyanate were employed. It is assumed that in films without copper thiocyanate, the sulfide radical can recombine via non-radiative recombination reaction. On the other hand, in the presence of copper thiocyanate, we expect that these trapped holes can be scavenged by the copper thiocyanate, as shown in this reaction here. This scavenging should give rise to a faster induced absorption recovery for the films employing copper thiocyanate. This is indeed what is seen as shown in this figure. Films of antimony sulfide in the presence of copper thiocyanate exhibit a faster recovery of the sulfide radical induced absorption than those where no copper thiocyanate is present. To obtain information on the rate of hole transfer, the induced absorption recovery was fit using a biexponential model, and the rate of the hole transfer was calculated from the average lifetime of the recovery as shown. From this, the estimated hole transfer rate constant from antimony sulfide to copper thiocyanate was calculated to be 5.9 times 10 to the 8th per second. From this study, it is seen that hole transfer from antimony sulfide to copper thiocyanate follows a two-step mechanism whereby photogenerated holes are first trapped in antimony sulfide as sulfide radical with an estimated rate constant of 4.5 times 10 to the 11th per second. Second, these trapped holes are transferred from antimony sulfide to copper thiocyanate with a rate constant of 5.9 times 10 to the 8th per second. These transient absorption measurements provide further insight into the mechanism of hole transfer in metal chalcogenide copper thiocyanate-based solar cells. It is also worth noting that the hole transfer measured in this study is 2 to 3 orders of magnitude slower than typical reported electron transfer rates in TiO2 metal chalcogenide systems. This indicates that these solar cells likely suffer from a slow extraction of holes compared to that of electrons. This further highlights two potential strategies for obtaining higher efficiency devices. First, a surface modification of the metal chalcogenide sensitizer could possibly enhance hole transfer rates and thereby reduce the buildup of photogenerated holes in the sensitizer. Second, a modification of the TiO2 antimony sulfide interface with a blocking layer could inhibit back electron transfer and recombination with the holes still stuck in antimony sulfide. Such strategies represent further challenges for the optimization and increased efficiency of solid-state semiconductor sensitized solar cells. This work was funded by the U.S. Department of Energy. If you are interested in learning more about the mechanism of hole transfer from antimony sulfide to copper thiocyanate, please refer to the full manuscript entitled Trap and Transfer, Two-Step Hole Injection Across the Antimony Sulfide Copper Thiocyanate Interface in Solid-State Solar Cells, published in ACS Nano. If you would like to learn more about the research happening in the Prashant Kamat laboratory at the University of Notre Dame, please visit our website at kamatlab.com or find us on Facebook at facebook.com/KamatLab. Thank you for your attention.